In this lecture, we will see the operation of a 2:1 mux. We'll draw the normal schematic using the transmission gate. Then we will draw the twisted schematic from the normal schematic diagram, and finally the layout. So now let's see the theory part of a 2:1 mux. This is a 2:1 mux. Mux is nothing but the multiplexer. So multiplexer is otherwise known as mux. So this is a 2:1 mux, which indicates that it has got 2 input and 1 output. Two is to 1 mux means it has got 2 inputs and 1 output. And we all know that if there are 2 to the power n number of inputs, 1 output in a mux, then the select line is, number of select line needed is n. So in this case, 2 to the power 1 is 2. So 2 to the power 1 input, 1 output. So the number of select line needed is 1. So what's a symbol or the structure of a 2:1 mux? So it has got 2 inputs, 1 output and 1 select line. So let's say the select line is S, input is I1 and I0. We can write it as AB, and the output is out. So if let's say this is 1 and this is 0, then the operation states that the operation of a 2:1 mux states that when the select line S is equal to 0, then my output will be I1, whatever the value of I1 will be, maybe 0 or maybe 1. When S is equal to 1, then output will be equal to I0. The value of I0 may be again 0 and 1. So now, in order to draw the schematic of a 2:1 mux, we need a pass transistor. So we need 2 pass transistors or the transmission gates in order to draw the schematic of a 2:1 mux. These 2 pass transistors or the 2 transmission gates are needed in order to pass the input, that is I1 and I0, depending on the select line value 0 and 1. So this 0 and 1 is a select line. So once it is 0, once it is 1. So when it's 0, when s is equal to 0, that means it is s bar. When s is equal to 1, means it should be s. And we can use two transmission gates. So when there are two transmission gates, so here we need an inverter. It is there should be s and s bar. So in a NOT gate we need one PMOS and one NMOS, and in the two transmission gates we need two PMOS and two NMOS. Need two PMOS and two NMOS. So now let's see the schematic diagram of a 2:1 mux. At first we will draw the two transmission gates, that is in this two side. This is the transmission gate 1, PMOS and NMOS. Similarly over here, and this is the second transmission gate. So we will connect these two, and these two will be connected. We need one inverter, so you can place one inverter here. This is a PMOS and MOS. These two are shorted. This is VDD, and this is ground. This is a select line S, and this is the select line S bar. So let's say this is S and this is S bar. So here at one point of input, this is the input of the transmission gate 1, output of transmission gate 1, input of transmission gate 2, and the output of transmission gate 2. So inputs will be I0 and I1, with the output will be shorted. So the control will be given at the gate, because we know gate is the controlling input. So at one point we have to give S, and the other point you have to give S bar. So S is given over here, and to this terminals S bar. So S bar is connected to S bar is connected to S bar is connected, and this is connected to this. Okay, and S will be connected over here. So this is S and this is S bar. Okay, now these are the inputs, I0 and I1. If you combine these two output, you'll get the final output from here. So this is I1, or this is I0, and this is I1, and this is the final output, that is out. We already know the various terminals, that is, this is the gate terminal, this is gate, and these are the source terminals, source and source, drain and drain, source, drain, this is source, drain, and source. Okay, so this is PMOS 1, 2, P1, N1, P2, N2, and P3, N3. So let us first see the twisted diagram from this normal schematic, and later on we'll see the operation of this multiplexer. So we have to twist these PMOS and NMOS in order to obtain the twisted schematic. So there are total 3 PMOS and 3 NMOS. So first draw the PMOS and NMOS. This is PMOS 1. This is PMOS 2. And this is PMOS 3. Similarly, this is NMOS 1. This is NMOS 2. And this is NMOS 3. So P1, N1, P2, N2. This is P3, N3. Okay. Similarly, we have the terminals. This is drain. Similarly, this is the source and drain. This is first transmission gate, then source drain, second transmission gate. This is again source drain and source drain. This is the inverter. So we know the gate, of course, from here. In the transmission gate, we know very well that the gates are connected in opposite. So we have to draw the transmission gate. We have to draw the schematic diagram in such a way so that it will be easy for us to draw the layout. So we can connect from here. Okay, so this is the the two gates are connected. Now the source of PMOS and NMOS of a transmission gate are connected. The drains are also connected. So connect from here to here and connect from here to here. Similarly, this is also the transmission gate. Source to source, drain to drain. Okay, now the source of the inverter is connected to VDD and the source of the NMOS source of the PMOS is connected to VDD and the source of the NMOS is connected to ground. The two grounds are the two drains are shorted, so connect this to. Similarly with the gate, so the input is S, that is select line. This is S bar. So as we know that in the first transmission gate, at the gate terminal, S bar is connected, that is over here. S bar is connected and to this S is connected. To transmission gate 2, S is connected. To transmission gate 1, S bar is connected. So S is connected to transmission gate 2. So this is poly and this is metal. Over here there is poly. S bar, this is poly, again poly. So directly can't go from here. Poly. This is S bar. This is poly and this is metal, so not a problem. Okay, S bar, and here S, this is also poly. Okay, so now you can see that there is an overlapping between metal layer and the poly layer. This is poly to poly, but here there is a overlapping between the metal and the poly layer. So here you have to place a poly contact in the layout. I'm just showing here. Okay, so now the only thing left is connecting the drains in order to obtain the output and giving the inputs. So this is I0 and this is I1. Okay, now the drains have to be connected. Okay, and this is the final output out. So this is I0, this is I0, this is I1, S and out. So here okay, from here we have to draw the layout of a twist to 1 mux. So in order to draw the layout of a twist to 1 mux from the twisted schematic, first you have to draw the PMOS, then the NMOS, and in order to draw the PMOS, first you have to draw the anvil. Okay, we can do one thing, we can clear this so that we can get enough space. So we'll draw the anvil first. So we need space for 3 P diffusion layer. So I think this much will be okay. So this is the anvil layer. Now after drawing the anvil layer, next you have to draw the P diffusion layer. So we need 3 P diffusion layer because we have 3 PMOS. So this is 1. Second one, and then the third one. This is the P diffusion layer. So now this whole is our PMOS. Now after drawing the P diffusion layer, next you have to draw the N diffusion layer. Most equal in area with the P diffusion. So this is the N diffusion layer. Now after drawing the PMOS and NMOS, now we have to label the source, gate and drain terminals. First two are the transmission gate, third is the inverter as we had drawn in the schematic diagram. So source drain and source drain, same as in the case of the schematic, so we need not mention it. So first we have to draw the inverter first. In the inverter, first you have to draw the gate so that we can apply the input. So the input to the gate is S, and the output will be obtained from the combination of from the drain of the PMOS and NMOS. This is the source, drain, source and drain. Source of the PMOS is connected to VDD. It's connected to VDD, and the source of the NMOS is connected to ground. Source of the NMOS is connected to ground. So this is connected by the metal one layer. Now after connecting the VDD and ground, next you have to connect the drain. And this is S bar. After constructing the inverter, so this is the inverter part is finished except the contacts. So you can complete the transmission gate, or if you want then complete the inverter first by placing the contacts. We need a p diffusion contact over here in order to make a contact between the metal and the p diffusion layer. Similarly over here, so this is a p diffusion contact, or you can say the PDC contact. Similarly, you need to place a contact over here in order to connect the N diffusion layer with the metal. So we need a N diffusion contact, or you can write it as NDC contact. After placing these diffusion contact, you can place the substrate contacts in the VDD and ground layer. So over here, this is the N substrate contact or the NWC contact. Similarly, in the ground, you have to place a P substrate contact. You can say PWC contact. Now you have to draw the transmission gates. So we know the gates are interconnected in the transmission gate. So first connect from here. Okay, next from here to here. Okay, now the gates are interconnected. So this gate is connected to S bar. The first gate is connected to S bar and the second gate is connected to S. Before connecting with the inverter, first we will complete the transmission gate. That is, this is the source, drain, source, drain, source, drain, drain. Know that the sources of the transmission gate and the drain of the transmission gate are connected. So still connected. Similarly over here. Okay. So now this is input I0 and this is input I1. These two are the output. So the outputs are connected from here. This is out. Okay. Now this control input S is connected to the first transmission gate, second transmission gate. So from here we can directly connect S. So S is directly connected and S bar is connected from here. In this way this can be connected. In this portion. So S bar is a metal layer. So we can directly connect like this from here. So since there is overlapping between a metal and a poly layer, we need to place a poly contact. So here we need a poly contact. So all the connections are done. Now you have to place the diffusion contacts. Here there will be a P diffusion contact. Similarly over here. All these are P diffusion contacts since these are the P diffusion layer. Here this is the N diffusion contact. N diffusion contact. This is the whole layout of a 2:1 mux from the twisted schematic. Diagram. Let's see the layout from the normal schematic diagram. Layout from normal schematic. normal schematic diagram of a 2:1 mux. So as we know, this much space will not be enough in order to draw the layout. We can do one thing, we can erase it. Before erasing, you can see the rough sketch. For example, this is the transmission gate 1 having the input I0, then transmission gate 2 having the input I1, where the output of the two transmission are shorted in order to obtain the final output. There is select line, here it's S and here it's S bar, and then we have a inverter where input is S and the obtained output is S bar, where S is connected over here and S bar is connected to this and S is connected to this. So now let's see the layout. When we say the normal schematic, first we will draw the transmission gates. So for that you need, this is the anvil, okay, then we need the P diffusion layer, okay, so this is the P diffusion layer, and then we need a N diffusion layer. So this is the N diffusion layer. Similarly, this is transmission gate 1. We have transmission gate 2. So similarly, this is N1, then P diffusion, and then the N diffusion layer. Okay, now after drawing this, we have to draw the inverter. So in our schematic diagram, the inverter was drawn in this form. Okay, or this can be raised and redrawn. Okay, this is the anvil. Then P diffusion. Similarly, the N diffusion layer. Okay, so now you have to draw the source and drain. This is the source, drain and source. This is the gate. So the gate of the PMOS and NMOS are connected. Okay. Okay. So this is inverter input, that is the select line S. This is the source of the PMOS which is connected to VDD. This is connected to VDD, and the source of the NMOS is connected to ground. Okay. So now, after connecting these sources, the two drains are connected in order to get S bar. So this is S bar, and this is metal 1. This is the poly layer. Okay, now before placing the contacts, or we can place the contacts in order to complete this inverter. Here we need to place a P diffusion contact in order to make a contact between the P diffusion and the metal layer. So this is P diffusion contact or EDC contact. Similarly, we have to place a P diffusion contact over here. This is a N diffusion contact. This is a N diffusion contact or a NDC contact in order to make a contact between the N diffusion layer and the metal layer. Similarly, a NDC contact is placed over here. Then after completing the diffusion contacts, you have to place the substrate contacts. So this is the N substrate and P substrate contact. So this is the N substrate contact. Or the NWC contact. And this is the P substrate contact or PWC contact. Contact or the PWC contact. Now, after drawing the inverter, let's complete the transmission gate. Now these are the source drain, then source drain, source drain, and source drain. Now these are the gate. We know that the gates are connected in a different way, so you can connect from here. Okay. Okay, now these two are connected. So this is S bar and this is S. So this S bar is connected directly over here. And from here we need a metal contact, metal layer from here. So there is overlapping between the metal and the poly layer. So we have to place a poly contact over here. So this is a poly contact. Now this S is connected to this, so we can connect like this. Now I can connect like this. Okay. Now after connecting S and S bar, you have to complete the connection between the sources and the drains of the transmission gate. The sources of the transmission gate are shorted, so source to source, then this is drain to drain. Similarly here, source to source. And drain to drain. This source is input 1, that is I0. This is input 2, that is I1. These two drains are connected to get the output, so we can connect from here directly. From here we'll obtain the output, that is out. Now the only thing left is the diffusion contacts. So here is the N diffusion, sorry, here this is the P diffusion contact. Since this is the P diffusion layer in contact with the metal. Here this is the N diffusion contact. Here again this is PDC. And this is NDC. Okay, so this is the layout from the normal schematic. From normal schematic. Now let's see the truth table of a 2:1 marks. The truth table of 2:1 marks. So the controlling input is the select line. So I write select or S, and the output is out. Okay, so when select is 0, then output is I1. Select is 1, output is I0. We have to check whether the truth table is correct or not. This I1 and I0 can have, it's a 1-bit value, so it can be either 0 or 1. So now let's see what happens if we apply this to the schematic. So in the schematic diagram, we have transmission gate 1, this is transmission gate 1, and this is the transmission gate 2. Okay, this is S bar, S bar, and this is S. This is input I0. This is I1. Let me short this too. This is the final output out. Now when S is equal to 0, then what will happen? Suppose this is P1, N1, this is P2, and this is N2. So when S is equal to 0, then S bar is equal to 1, S bar is equal to 1. So here PMOS 1, at PMOS 1 we have 1, at NMOS 1 we have 0. As we know that if input is 0, then PMOS is on and NMOS is off. If it's 1, then PMOS off and NMOS will turn on. So when S is 0, you can say there is a reverse condition. So P1 and N1 will turn off. That means the transmission gate 1 is inactive. This is the transmission gate 1. This is the transmission gate 2. In transmission gate 2, you can see here at P2, 0 is applied, at NMOS, 1 is applied. So P2 and N2 will turn on. That is, transmission gate 2 is active. When transmission gate 2 is active, then the input I1 is seen at the output. So out is equal to I1. I1 can have any value, that is, if it's 0, then out will be 0. If 1, then out will be 1. So whatever the value of the I1 will be there at that point will be seen at the output. So when S is equal to 0, then out is equal to I1. So this is verified from the truth table. This was the first case. Then the second case is when S is equal to 1. When S is equal to 1, first draw the schematic. Okay. This is transmission gate 2. These two are connected. So this is S and this is S bar. Here it's S bar. This is I0 and this is I1. Output out. So now this is P1, N1, P2, N2. Now when S is equal to 1, that is S1, means S bar will be 0, S bar will be 0. So we know that when input is equal to 0, then the PMOS will be on and the NMOS will be off. If it's 1, PMOS will be off and NMOS will be on. So now when input is 0, when S is equal to 1, in the transmission gate 1, this is TG1 and this is TG2. In TG1, in transmission gate 1, you can see that at P1 0 is applied, that is at PMOS 0 is applied, and at NMOS 1 is applied. So P1 and N1 will turn on, that is transmission gate 1 will be active, while in the transmission gate 2 S is 1, that is P2, at P2 1 is applied and at N 0 is applied. So P2 and N2 will turn off. That is transmission gate 2 is inactive. Okay. Now when transmission gate 1 is active, then the input I0 will pass to the output, since these two will be short circuit. On means short circuit, off means open. So at out we obtain I0. Even here also I0 is a 1-bit value. It can be 0, it can be 1. If I0 is 0, then at output you'll get 0. If I0 is 1, then at output you'll get 1. So when S is equal to 1, then out is equal to I0. So this is also verified. If you want at S1, when S is equal to 1, the output should be I1, and when S is equal to 0, output should be when S is equal to 0, out should be I0. We have to just replace this by I0 and this by I1 and this by I0. So the function of the mux over here, out is equal to S into I0 plus S bar into I1. This is the function of the 2:1 mux. The function of the 2:1 mux.